In this video, we're going to look at curvilinear motion using normal and tangential components. These are often used if you know the path of the object. When path is known, we can use, say, tangential components, and that would be like the velocity tangential to the path. So let's say this is the path here of the object of the particle. And using the tangential velocity. Usually when we say v, it'll be the tangential velocity, since that's really the only velocity in this context that we'll have. And then we'll also have a tangential acceleration, and we'll have a normal acceleration. So again, if something moving along this path, we'll have a tangential velocity, a tangential acceleration, and a normal acceleration. Remember, the normal component is perpendicular to the path. And the tangential acceleration is, of course, simply going to be the derivative of the velocity with respect to time. And the normal acceleration is going to be that tangential velocity squared divided by rho. And rho is the radius of curvature of the path at the point under consideration. And then, as usual, the acceleration then can be calculated by taking the square root of the sum of the squares of the normal and tangential components. And sometimes we'll need another relationship. We'll use AT ds is equal to V dt. Excuse me, dV. These is equal to V dV, like that. So now this radius of curvature, this is going to depend on the type of curve that we have. If we have a circle, the radius of curvature will simply be the radius of the circle. If we have a straight line, then the radius of curvature is essentially infinite. And that means, so this is the limit of this is infinity. And so the normal component of acceleration will be 0. On the other hand, sometimes we're given a more general curve that's not a circle, not a line, and we have to calculate it, the radius of curvature ourselves. So let's take a look at that real quickly. The radius of curvature, if we have a circle, and we have a circle, again, a radius r, then rho is simply equal to the radius. If we have a straight line, you can kind of imagine that, that there's no center of the radius of curvatures. It's basically infinite. So if you have a straight line, this is going to not equal to, but we should technically say it's going to approach infinity. And so that means, so in that case, we can just simply say the normal component of the acceleration is 0. And for a general curve, when the path is given as a function of x, so you have a path out here like this, your particle is going along this path, and it's described this way, then the radius of curvature can be calculated. Like this. Now, one thing to keep in mind, and this is sometimes will be used, is that just like you had from calculus, dy dx is the slope of the tangent line. Of course, at a particular point. So we're going to use this very often when we have the equation of the path given. We could find the radius of curvature using this equation at any particular point. So let's take a look at some examples. So let's take a look at this problem. It says the box of negligible size is sliding down along a curved path defined by the parabola y equals 0.4x squared. When it is at A, the coordinates are x equal 2 and y equal 1.6. The speed is 8 meters per second. And the increase in speed is dv dt equals 4 meters per second squared. Determine the magnitude of the acceleration of the box at this instant. So notice that the equation for the path is given by y equal 0.4x squared. And we're also given the point at which we're to calculate the acceleration, x equal 2 and y equal 1.6. And so we're also, notice we're given the velocity. The velocity is 8 meters per second. And we're also given the acceleration because remember, dv dt is the acceleration. And that would, of course, be the tangential acceleration. So that'd be dv dt is equal to 4 meters per second squared. So we have a lot of the information already given. Now, we don't know the radius of curvature, so we're going to have to calculate that. And we're going to have to use our equation because we're given the path, and we're going to have to use the equation with the derivatives in. But before I calculate that, let me take those derivatives. So y is given as 0.4x squared. And then dy dx, we bring this down, would be 0.8x. And the second derivative is 0.8. Now, there's several ways you could do it at this point. You could evaluate these at 2, and maybe that would be the easiest thing to do. Let's do that. Let's evaluate these things at 2. Now, actually, if we put 2 in here, we already know what the answer is going to be because we're given that 1.6. But let's just check that. 2 squared. That's going to be 0.4 times 4, which is 1.6. That one was given. Now over here, if we put in 2 for x, as it turns out, that looks like that's also 1.6, just happens to be. And of course, this one is just 0.8 no matter what x we put in. So now let's calculate our radius of curvature. Again, we're going to be using this equation. And now you could have gone ahead and put these in with the x's included and then substitute x equal to, that's up to you. What I choose to do in this case, I put the 2 in first since I knew that's where we wanted to evaluate it. And then, so now we can calculate this. So if we put 1.6 here, and we put the second derivative down here. Notice that the absolute value of the second derivative, but since it's already positive, we can just leave it positive. We don't have to do anything. And so we put this in the calculator. For the numerator, I got 6.72. And for the denominator, of course, there's 0.8. And so when we divide this out, we get about 8.396. You can call that 8.4 meters is close enough. That's going to give us our radius of curvature. Now we can calculate our normal acceleration. It's v squared over rho. And then remember, we're given our v, our velocity. And divide this by 8.4. It's around 7.62. I've rounded things a bit here, so 7.62 meters per second squared. And then finally, if we want the overall acceleration, it's going to be the square root of an squared plus at squared. And again, the at was given to us. This we just calculated. That's around 8.61. Meters per second squared. So again, that problem pretty straightforward because we were given the path, which was our 0.4 x squared. We found the derivatives. And like I said, you could have put the 0.8 x in here and the 0.2 here, then substitute the x later. That's up to you. I put in the x equal 2 first before I substituted, and I got a radius of curvature. And calculated the normal component. The tangential was given to us, and found the acceleration. Next, let's take a look at this problem, 12-134. 12-134 says the motorcycle is traveling at a constant speed of 60 kilometers per hour. Determine the magnitude of acceleration when it is at point A. So once again, the path of the object of the motorcycle is given as y squared is equal to 2x. And also the point that we're interested in is given. Notice that it's 25 meters, so it's going to be x is going to be equal to 25. So again, the path is given as y squared equal to x. We're given the velocity, which is constant, and the point is given. Now, you can work with kilometers per hour. Usually I convert that to meters per second. So let me just do that. So if it's 60 kilometers per hour, that would be 60,000 meters per hour. Now, if we divide that by 3,600 seconds per hour, that'll give us 16.67 meters per second will be the velocity. Again, that's always the tangential velocity. And notice one thing here, it's constant. So the velocity is constant. That's telling us that the tangential acceleration is going to be 0. So now we're going to need to find the curvature. So let me take the derivative of this, and let me rewrite that first. So let me rewrite that as y equals the square root of 2x to the 1/2. I just took the square root of both sides. Now, normally we would have a plus or a minus here, a plus and a minus here, but the minus would indicate a point earlier. It would have been like earlier in the past. So we'll ignore the negative here. And we'll go ahead and take derivatives, dx, the first derivative, dy dx. Take another derivative. And that'll be negative square root of 2 over 4x to the minus 3/2. So again, we can put this into our equation for the curvature, or we can just plug the x values in. Now, let me do that. I don't know if we actually even need the y value here, but let me just calculate it anyway. This is going to give us the y component of the point at which we want our information. And of course, that's just going to be the square root of 25, which is going to be 5. Times square root of 2. That gives us 7.07 meters. And do the same thing over here. That's going to end up going in the denominator. That'll be the square root of, that'll be square root of 25 in the denominator, which is going to be 5. And then times 2, and then divide it into the square root of 2. That's going to be 0.01414. And I probably should put in exactly what I was doing here. Let me just show that. So what I did here was put in 25. Again, the point 25 to the negative 1/2. And it's 0.1414. And then same thing down here. And this is 25 to the minus 3/2. This is going to be negative 0.00283. So now we have everything we'll need. We'll put everything into our radius of curvature equation. this. This up here. We have 283. Now, of course, when we take the absolute value here, that's going to become positive. And so let's put that into our calculator. And we get around 364 meters. It's going to be our radius of curvature. So finally, we want to find the normal acceleration. Our normal acceleration, remember, is our velocity, which is always tangential velocity divided by rho. And we found that to be 16.67 meters per second. And then we have to square those. Be 64 meters. Seven, 6, 3, 4 meters per second squared. That's our normal acceleration. And actually, if you wanted again, the total acceleration, that's going to be a t squared plus a n squared, but the at squared 0. So in effect, what it's going to be, overall acceleration is just going to be the absolute value of the normal acceleration, since there is no tangential. And in this case, since it's positive, it's going to be the same. Like that. Next, we're going to take a look at this problem. When x is 10 feet, the crate has a speed of 20 feet per second, which is increasing at 6 feet per second squared. Determine the direction of the crate's velocity and the magnitude of the crate's acceleration at this instant. So this is very similar to the previous problem. Just ask us one extra thing and ask us for the direction of the velocity. And we're usually not going to have to find that, but it's pretty straightforward to find. So we'll do that here. Again, usually we won't need to do that. But let's go through the normal steps. We're given the path. So we have y equal 124x squared. And we're going to need the derivatives. And when we bring that forward, that's going to be 2 over 24, which will be 1/12 x. Then the second derivative is going to be simply 1/12. And let's evaluate it, the point given. And sometimes I probably should have done this on the other ones. Maybe will put down here, where we're evaluating this derivative at x equal 10. You don't have to do that. I didn't do that in last example, but sometimes it's helpful to keep in mind we're putting a 10 in for x. And this is 4.167. 10, which is 5.6. And I don't know, we can keep it. It might be helpful to keep it that way because we're going to use that in a minute. Again, now usually we don't have to note this, but again, remember, the first derivative is always the slope of the curve. And then finally, let's go to this one. It's going to be 1/12. And so let's do our usual stuff. Find our radius of curvature. Excuse me, let me get a little ahead of the game. Let me just put I always like to write the equation down while we're still learning it. And so then just substitute our values. And for dy dx, we had 5.6. For the second derivative, 1/12. And when you put all that in your calculator, you get 26.5. And we're working in feet. And so that's our radius of curvature. Now we can calculate our normal acceleration. That's going to be, of course, our velocity squared over rho. We're told our velocity was 20 feet per second. Divided by 26.5. That's about 15.11 feet per second squared. Then our acceleration is going to be the square root of the normal and tangential squared. I neglected to write it down, but our tangential acceleration was given, and that was given as 6 feet per second squared. That was actually given in the problem. And so this is going to be square root of 6 squared plus 15, 11 squared, square root of that. And our acceleration comes out to around 16.26 feet per second squared. So again, the only thing extra that this problem asked us for was the direction of the velocity. So let me just take a minute and look at that. And now notice, as I said, the dy dx gives us the slope at the point we're interested in. So let's take a look at that for a minute. So we have our package here. And the slope is 5/6. And remember what that means. That means rise over run. And so you can maybe sort of think of it, maybe we could sort of think of it like this. So the slope is rise over run. So it's going to be 5 is the rise. 6 is the run. So if we want the direction or the angle, it's a tangent of theta is equal to the opposite over the adjacent. So to find theta, we can take the inverse tangent. And when you put that into your calculator, you get around, I have it in radians, obviously. We put that into your calculator. You get around 39.8 degrees. So that's the only little extra thing that was given in this problem that we're asked to do. Usually we don't have to do this, but if you are, use the fact that you know this derivative is the slope, and then you're given the slope, you make your little triangle, you can say, okay, that package is coming down at an angle of 39.8 degrees from the horizontal. Again, this is going to be the direction of the crate velocity. Next, let's take a look at this problem, 12-125. The car travels around the circular track having a radius of 300 meters, such that when it is at point A, it has a velocity of 5 meters per second, which is increasing it at a rate of 0.06 t meters per second squared, where t is in seconds. Determine the magnitudes of its velocity and acceleration when it has traveled 1/3 the way around the track. So we have this car going around the circular track, and it has a radius of 300 meters. That's a constant radius, so we can call our radius of curvature 300 meters. And we know the velocity at point A is given as 5 meters per second. And then V dot, which of course V dot is going to be the acceleration. Again, the tangential acceleration is V dot, and that's given to be 0.6 t meters per second squared. And we're going to need to find information when it gets to point B. So first we might want to find out, what is the distance? What is this distance S, to go from point A to point B? What's this total distance right here? Again, we'll call this S. So that distance S is going to be, of course, equal to the circumference. And the circumference, remember, is 2 pi r. So 2 pi times 300 meters. But we're only going a third around. So we'll multiply that by a third. And those are going to cancel. So we end up with 2 times 100 pi, so it's 200 pi meters. So that's going to be how long a distance it's going to get to point B. So we just needed to do that, and then most of the rest of the problem, we're going to need to find an equation for the velocity. So we're given that the acceleration, or the v dot, is this. So we know that dv dt is equal to 0.06 t. And then we can do this, just find the equation for velocity. We'll go ahead and integrate this. We're starting at time 0 to t. Then now the velocity here is starting at 5. So we're going to integrate this from 5 to v. So integrate this left side, we'll get v, then we put v in, and minus 5 for the lower bound. There's going to be 5 for the lower bound, but we'll be subtracting 5. And over here, this will be squared divided by 2. Like this. And then we can rewrite this and bring the 5 to the right-hand side. It'll be a little bit easier to work with. And we can call this equation 1. And now we want the equation for distance, or position. I guess actually position would be the proper one. So again, we know that the SDT is equal to the velocity. So if we rewrite this like this and put our velocity into here, And again, we're starting at it times 0 to time, to some time t. And again, our position, we'll call that the starting point 0 to s. Integrate this. The lower bound is going to be 0, so it'll be minus 0. And the right-hand side, we're going to get t cubed divided by 3. And so that'll be t cubed. And that'll be 0.01 in front. Let me just make that a little bit nicer. Plus 5t like this. And it's equation 2. Again, so this would be the position S, and so it's going to be along that path. And so we have this equation here. And so we would like to find out at what time does it get to point B? If we knew that, then we could find other information. So to find what time to get to point B, we know that point B, we calculated that to be 200 pi meters from A. So if we put 200 pi in for S, we can solve for T. So substitute S equal 200 pi into equation 2. Now give us 200 pi is equal to 0, 1, 2 t cubed plus 5t. Now, cubic is very difficult to solve. If it was equal to 0, then we could just factor out a t and then have a quadratic equation. So, but we can't do that. There is a cubic formula, but it's kind of difficult to use. I usually will just put this in my calculator. So what I'm going to do here, I'm going to put 0.01, and now my calculator uses x's, so I'll put x cubed plus 5. Oh, so I left off a t here, excuse me. I'll put in 0.01 x cubed plus 5x minus 200 pi. So I put in something, I don't know if you see that in the calculator, 0.01 x cubed plus 5x minus 200 times pi. So I put in that for my equation. And so to solve for t, I put that as that is going to be like my y value. Y equals this equation here. And then find the point where y is 0. So I'll go ahead and plot that. Now I'll use maybe 0, x equals 0 to 100, because I don't know exactly what the answer is going to be. And then I'll use y from maybe -10 to 10, because all I want to do is find out where y is 0. So I just need to find where it crosses the x-axis. So I'll graph this, and I get this, looks like it's almost a vertical line. So we'll have to sort of zoom in a little bit. So I'll put on the trace and find about where that X value is, where that's occurring. I don't know where, let's see where, I'm just hitting this here, waiting for the X. Let me see, where is it going to show up? Well, it looks like, if you look down here, it looks like Y is positive for 25, and that goes negative when you go down to 35. So it looks like our solution's somewhere between 35. Let's see, excuse me. Yeah, so Y is 25 when X is 36. And then Y is negative when X is around 35. So it changes from negative to positive somewhere between 35 and 36. So what I'm going to do, I'm going to cut down my window, maybe go from 35 to 36, and then graph that. See, yeah, so that gives you an idea. So you have to often close in on this a little bit. Now I'll hit the trace here. Now we can actually see our little object here and see about when it gets to 0. It looks like it gets to 0, right there, Y is just a little bit above 0, and X is about 35.59. If you wanted to, you could really close in on it more. We could maybe go, let me go 35.5 to 35.6 and see what happens. 35.5. You don't usually have to get this accurate, but if you have sometime you need to, then we can actually see where it's crossing a little bit better. Let me put the trace on again. Yeah, it looks like we're getting really closing on. We're getting at 0 about 35.58. And now remember, we are solving for t, so that's going to actually be a t. 35.58 seconds is going to be the solution to this. Now we can find everything else. If we want to find the velocity, so sub this value into the equation 1. And I got about 42.87 meters per second. And then if we want the tangential component of acceleration, that was given up here. So AT is given by 0.06 t. And if we put this t value into that, I get around 2.13 meters per second squared. Then if I want to find normal acceleration, that's going to be v squared over rho. 42.87 squared divided by, remember, rho is just the radius. That was 300. And that's about 6.126 meters per second squared. Then finally, if you want the magnitude of the acceleration, we're going to put a n squared plus a t squared. And was 6.126 squared. And then 2.13 squared. And put that in your calculator. And I'm rounding this a bit. So it's 6.487 meters per second squared. So there you have it. This is, again, very similar to the other problems. The only difference here is that we were given a point. We were told, it was going to be a third way around the track. We had to find S, and then we had to use the equation for position to find out what time it got to that second point. That point we call B. So we plugged it in there and then plotted it and, found, remember we put into the calculator and plotted and found that. And once we found the time, that was the time at which we got the point B, then we could use that time along with these equations to find, particularly use this equation and this equation up here that we were given to find the velocity and the acceleration.